All right, so negative pressure breathing is also referred to as tidal ventilation. Tidal ventilation, meaning the tide goes in, the tide comes out. So what we have here is a system, right, where air comes in and air goes out back through the same tube. In through the tube, out through the tube, into the tube, out through the tube. So we have this process called tidal ventilation. Because we ventilate tidally, we can't set up a countercurrent system, right? Because there is no way to kind of predict where the air is going to move once it gets to the alveoli. Once the air is in the alveoli, we can't really set up a countercurrent exchange system, which means we're really not optimizing the amount of air that's moving, optimizing the amount of oxygen and CO2 that are moving across that respiratory surface. So I'm going to do a little bit of terminology here, and then we're going to talk about birds who have kind of solved this problem and can get much more efficient gas exchange. Okay? All right. A few terms here let's talk about. So the volume of the air that is moved in and out through the lungs, inhaled air is air coming in, and exhaled air is the air that's moving out. This is referred to as the tidal volume. Okay? That tidal volume at rest, right? Me on the couch not doing anything, that's at rest. We're talking about 1/2 liter of air is being moved in and out through tidal ventilation. Okay? Now, under load, right, we need more air because we have increased metabolic demand. I can increase the amount of air that's inhaled and exhaled. So this we're going to refer to as the maximum tidal volume. How much air could you move in if you really wanted to? This maximum tidal volume is called the vital capacity. And the vital capacity for somebody your age, I got some numbers for typical college students. Typical female college student, you're talking about 3.4 liters on average is the amount of air that's moved in and out. And for males, college aged, about 4.8 liters on average. Okay? All right, now, the maximum air that you can move in and out is not the same as the air that the lung holds. The lung can hold more air than can be moved in and out. And if you think about it, there's no way for us to completely clear out all of the air within the lungs, right? There's always some residual volume, which is the air left over. This is called residual volume. Okay. Or the other way to think about it is the vital capacity plus the residual volume would give us the total amount of air that the lungs actually hold. That's the maximum amount that you can move in and out. There's always some left over. If you removed all the air from the lungs, you'd have a big vacuum in your lungs and everything would collapse on itself, despite all those cartilage rings. Okay? All right. Okay. Let's go ahead and move to the birds now. The idea is we can't, when we do this kind of tidal ventilation, you can't really control the arrangement of the circulatory system relative to the respiratory membranes. But what if you could design a system that could do that? And that's where the birds come in. The birds have kind of solved this problem of a countercurrent system with tidal ventilation by coming up with this system. So this is what it looks like in 3 dimensions. There's the lung itself, which is kind of here, and then associated with the lungs are these sacs, right? Posterior thoracic sac, anterior thoracic sac, abdominal sac. And these sacs are important in making the air move in the proper direction across the respiratory surface. But it's hard to talk about in 3 dimensions. So what let's do is let's switch over to a 2-dimensional image of these. These air sacs just represent a few of the air sacs, and then these tubes just represent some of the tubes that occur within the lungs. So here, that's the trachea. That's the air coming in. And I'm just going to kind of recreate this diagram. Okay. So that's the trachea. That's where the air is going to come in when we inhale and where it's going to go out when we exhale. Okay. Air sacs here. And then let's label some of this stuff. The trachea eventually is going to start to branch into a bronchus. And then here, this is referred to as the mesobronchus. And then here, these are parabronchi. Okay? All right, so this is how this works. Let's increase the size of the thoracic cavity. As we increase the size of the thoracic cavity, air should be pulled into the lungs. So air is going to move here. Not easy for it to move that direction, but it's easy for it to move this direction. So as it does, the air moves into the air sac. The air sac is expanding as the thoracic cavity expands. Same thing here. This air sac is expanding. That's going to pull air from these parabronchi into the air sac. Okay? Now, by doing that, I'm forcing the air to move in this direction across the respiratory surface, which means I just need to run the blood in this direction, and I've got a nice countercurrent exchange. So I have tidal ventilation mixed with countercurrent. Okay, all right, now decrease the size of the thoracic cavity. So, okay, decrease the size of the thoracic cavity. I'm going to end up squeezing on these air sacs. Air is going to get pushed this way and this way. Okay, so this air here, right, so I squeeze on that, air gets pushed out, and then I increase the size of the thoracic cavity, air gets pulled like this, squeeze it out, air gets moved like that. So I end up with this weird kind of circular movement of air, right? So that I'm always moving air across those parabronchi respiratory membranes in the same direction. And by doing that, I get to take advantage of the countercurrent system. I can increase the amount of oxygen and CO2 that can diffuse across the respiratory surface. This is not trivial. Birds are much better at optimizing the amount of diffusion that can occur with these gases because of this arrangement. That means they can work under heavier loads. Imagine you're a bird and you're flying south for the winter. That's a lot of metabolic demand. Well, you can meet that metabolic demand by increasing the delivery of oxygen to the tissues. You even have those geese that can fly over the top of Mount Everest. they're flying over the top of Mount Everest where there isn't a lot of oxygen, well, they optimize the amount of oxygen that gets delivered to these tissues. Okay? All right. Now, basically what we've just finished as part of gas exchange was this concept of ventilation. Ventilating gills, using a tracheal system, ventilating lungs through positive pressure breathing, ventilating the lungs through negative pressure breathing. Now, along with this ventilation, let's actually talk about the gas exchange itself, right? How can we get those gases to actually exchange? Okay? Now, when we talk about the movement of gases from one place to another, so far I've been talking about the movement of gases being driven by diffusion. And that's kind of correct. But really what we're going to do to determine the direction of diffusion and how much diffusion actually occurs is by talking about what's called the partial pressure of the gases. The partial pressure of a gas. Let's wait on that. So we think about all the gases that are in a particular amount of air. So if I had a liter of air here, there are a bunch of gases that are included in here. And the gases would be bouncing around inside this liter of air, and the bouncing around, right, the movement of these molecules is generating a pressure on the inside of this liter of air. And the amount of pressure that each of these gases generates depends on the amount of the gas within this liter. So all I would have to do is figure out, well, how much of this air is oxygen? And that would give me the partial pressure of oxygen. How much of this air is CO2? That's the partial pressure of CO2. How much of the air is nitrogen gas? That's the partial pressure of the nitrogen gas. Okay? All right. The other way to think about it is with a person standing down here, and there's a particular amount of air above this person generating pressure on top of this person. The amount of pressure generated on this particular person when the person is standing at sea level, we quantify this amount of pressure as 1 atmosphere. Okay, 1 atmosphere of pressure, that's the combined pressure of all these gases pushing down on this poor guy's head. Is that right? Okay. Now, 1 atmosphere is also equal to 760 millimeters of mercury. It's Hg, right? This is the older unit of measurement. We talk about atmospheres now, but in the old days they had barometers that could measure pressure using mercury. So 760 millimeters of mercury equals 1 atmosphere. And then I believe in chemistry they might still talk about it, torr. I think that's also equal to 760 torr. Yes, no? Okay. All right, so let's use millimeters of mercury here. So if I've got 760 millimeters of mercury total pressure, I could figure out the partial pressure of oxygen. And let's call that P of O2 for partial pressure of oxygen. And at sea level, the partial pressure of oxygen should be 160 millimeters of mercury. Okay? Or, if I did this math, right, the partial pressure due to oxygen divided by the total pressure would tell us that that's roughly 21%, which should be roughly the amount of oxygen as a percentage of that gas. So of this gas weighing down this person here, 160 millimeters of this pressure is due to the oxygen. The remainder is due to the other gases that are there. Since oxygen comprises 21% of the overall amount, it comprises 21% of the pressure that's generated by that total gas. Okay? All right, the partial pressure of CO2 is much lower because there's a lot less CO2 in the atmosphere. There's 21% oxygen. I think we're at about 0.035, somewhere in there, percent CO2. That means that the partial pressure of CO2 is 0.23 millimeters of mercury. Okay? All right. Now, in order to exchange gases, we've said that the respiratory surface needs to be wet, and therefore we're talking about water containing these gases, or these gases solubilizing within the water in order to diffuse across the surface. So the amount of gas that will dissolve in water is proportional to its partial pressure as well as its solubility. Right? So somewhere in chemistry, I don't want to go back through this again, I hate to mention the name chemistry, but in your chemistry class, they should talk to you about solubilities, right? Solubilities of gases are typically pretty low. They don't like to be dissolved in water, and it gets harder and harder to dissolve them as the temperature increases, right? But in any event, the partial pressure helps determine how easy it is to go into the water, along with the solubility of the gases. Okay? If I remember right, CO2 has a lower solubility than oxygen. Okay? All right. Now, as the gases, in particular oxygen, moves into the water, that should continue to happen until an equilibrium is reached where the partial pressure of the oxygen in the water equals the partial pressure of the oxygen in the air. And the same thing would be true for CO2. It would stop